Hey, welcome guys. So in order to welcome. So this is my first video about the Galois theory. And in order to explain the fully detail of Galois theory, may be very difficult. So I may spend I will spend like at least 10 videos or 20 videos about the Galois theory because it's very beautiful. And I hope you guys subscribe to my channel. So I will post so basically most of them follow the Hurston and also other like abstract algebra. And basically I will post the reference below. But in this video, I will want to first introduce the important idea called the symmetric polynomials. And we will use this the main theorem in the symmetric polynomial so that we can in the future then we can use this. So this is very important idea. And there is a main theorem in the symmetric polynomials which we will always keep use when we try to solve the polynomial equations. Okay, so let me just quickly start. Hope you guys subscribe to my channel. Okay, so imagine that you have, let's say, x1 up to xn, and you can define s1, x1 to xn, which is the first symmetric polynomial, which is the summation of xi, I from 1 to n. And also you can define s2, x1, x up to xn, which is a summation of xi, xj, which I less than j. So basically, this is just the pair, the x1, x2, x1, x3, yeah, and also x2, x3. And also you can define S3 to be I less than j less than k, xi, xj, xk. Okay, and then you can define the final one should be Sn, right? So the Sn should be x1, x2, up to xn. Okay, and this is called elementary symmetric polynomials. Symmetric polynomials. Okay, so why this is special, right? So for example, okay, so let's consider this very simple symmetric polynomial like x1 up to xn squared. Okay, so you can see that this guy is symmetric. So I haven't defined what it means by symmetric polynomial. Suppose you have a polynomial which x has the variable x1 to xn, which is the same as you make the permutation, which is the sigma 1, x sigma 2, x for sigma n, where sigma belongs to the symmetric, the permutation of n letters. So for any sigma belongs to the symmetric permutation with n letters. Right, so for example, you can permute this x1 up to xn, then this guy is the same. But notice that this f is not the same as any particular symmetric polynomials. But obviously that you can write this as x1 up to xn squared, and then minus 2 the products, right? So you can write as this. Right, so this guy equals to s1 squared minus 2s2. Okay, so this tells you that it seems like that these symmetric polynomials can be written as some combination of the elementary symmetric polynomials. Okay, so this is the main theorem that I try to prove in this video. So let me just write down. So sometimes this is called symmetric. I think this name is not regular, but usually people told that this is a symmetric polynomials. This should be viewed as the elementary symmetric polynomial theory. Okay, so let's take for every symmetric polynomials, f, which is symmetric polynomials, belongs to A, which is x1 up to xn, which this is a polynomial ring, where A can be used to commutative ring with identity. Okay, so usually you can take A to Q or R. Usually it's a field, right? But sometimes you will need integer version. Okay, then there exists the G belongs to A, x1, x2, up to xn. such that your f is equals to g, right? So your f is equals to g for plugging s. So g is a polynomial, right? Plugging s1, s2 up to sn. Okay, so for this is a simple simplest example is what I just said. Your x1 up to xn squared is a s1 squared minus 2s2, right? So in this case, your g can be just written as the x1 squared minus 2x2, and then you replace each x1, s2 to be s1, s2. Okay, so this is so every symmetric polynomials is can be viewed basically is the element of the polynomial ring, but with the variable of elementary symmetric polynomials. Where this is just this. Okay. Okay, so let's talk about the proofs. Okay. Okay, so this proof is a little bit using the somehow like algebraic geometry idea that grab on the basis. So basically, the idea is that we want to reorder order a basis. Right? For example, let's define x alpha. So alpha is a vector, which is defined to be, let's say, defined by x1 alpha 1, x2 alpha 2. Let's say this is Sn alpha n. Sorry, so this is a short notation that I call x alpha. Right. So for example, maybe you can use x1 5, x2 7, or x4. Okay. But basically, you can write this as x1 5, x2 7, x3 0, and x4, and the rest are all 0. Okay, and then you can define x alpha less than s beta if and only if. Okay, so if you want to compare these two, then you can write this alpha as a vector, right? Basically alpha 1, alpha 2, alpha n, and then this beta is beta 1, beta 2, beta n, and then you start to compare, right? So if alpha 1 greater than beta 1, sorry, I think if it's okay, so if they are the same up to something, okay, and let's say up to alpha k, there's this alpha n, beta n, up to alpha k, and there is some difference. For example, this alpha k less than beta k, then we say beta greater than alpha, right? So everyone start to compare with the first guy. So the highest x1 power will belong the largest one, and then keep going, keep going, keep going. Okay, and you can easily check that. You can easily check what? You can easily check that if x alpha less than s beta, then the x alpha plus gamma will less than x beta plus gamma by definition. Okay. Okay, so let me just say one example. Okay. Okay, so this example is also trivial. So let's consider s cube, which greater than, so cube is 3, 0, 0. Let's say I only have x, y, z, 3 variable. So cube 3, 0, 0 will greater than, let's say, x squared y, which is 2, 1, 0, which greater than, right? Greater than what? Greater than x squared z, because everyone start from highest, right? So 2, 0, 1, and the greater than x y squared. Now the x is only 1, right? So this is 1, 2, 0, and less than x y z. This guy is 1, 1, 1, and greater than x z squared, greater than y squared z, and final is that y z squared, right? So this is the smallest for the degree 3. So this is 0, 1, 2. Okay, so just using this. Okay, so now we can do the proof. So proof is very strange that some guy can think about this kind of thing. Okay, so now given f, which is a symmetric polynomials in this polynomial ring. Okay, so right, so I can order these spaces and pick the largest one, right? So let's say f is a q x alpha. So this is the highest term in terms of this, right? So I can find the highest term. Let's say coefficient is q. So this q be some coefficient which belongs to a. Okay, with the rest. Okay, so how can I write this x alpha in terms of symmetric polynomials? Okay, so remember that our symmetric polynomial s1 is x1 plus da da da, x2 is x1, x2 plus da da da, s3 is x1, x2, x3 plus da da da, sn is x1, x2 up to xn. Okay, so you notice that this is x1, 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 x1. Okay, so that means what? So I can write the leading term to be q x1 alpha 1, x2 alpha 2 up to xn alpha n. Okay, now I try to make this guy match with the highest term. Okay, so what should I do, right? So I can make this q, right, in terms of s1, right? So x1 go to the highest power, so s1 to alpha 1, and x2 to be this, right? x2 need to contribute another, so s2. Oh, sorry. So let's see. So in order for make x1 okay, in order to make this x1 match with this alpha 1, what I should do is that let's say I get s1 alpha 1, right? So I get something which is alpha 1, right? The highest term for x1. And but if I pick as x2 to be s2, then then let's say, right, so s2, let's say s2 alpha 2 will give me x1 alpha 2, x2 alpha 2, right? So you know I want to kill this guy, so I should use s1 alpha 1 minus alpha 2, and s2 alpha 2 minus s3. So remember, by definition, this is the highest term, right? So you will cancel this term. Okay, cancel this. And then also for s3, you just keep going, alpha 3 minus alpha 4. Okay, and until what? Until what? Until this guy finally become like s n minus 1 alpha n minus 1 minus alpha n, right? So final has s1 s this, so this is small n, so this guy is sn alpha n, right, plus some term. So this term contains x1, so the power of x1 is alpha 1 minus alpha 2 plus alpha 2 minus alpha 3, right? By this. Also s1 has I think alpha, but if you sum over, you can check the alpha 1 term, right? So alpha x1 term contains alpha 1 power, and x2 term start from here, right? I mean, you can check it. So s2 term start from the alpha 2. Okay, but basically this matches with the what we have did for the definition, right? So everybody start from this term. Okay, so after this, okay, so after this process, let's see. Okay, so after this process, we eliminate the highest term. Okay, so now your f, right? If you use f minus this q times this, right? So after this still belongs to the symmetric polynomial, right? Because this guy is symmetric, still symmetric. But then what? But then the highest term disappear, right? But then highest term disappear, and you can keep going. So we can keep going. So always, so since f is finite polynomial, right? So always terminate. Right? So one each you keep going, and finally you prove that f is the polynomial ring. F is written as symmetric polynomial ring. Yeah, this is the proof. Okay, so let's see some example. So let's see one famous example. This example is famous, right? I think everyone knows about this. When I was high school, that my teacher told me this is true, and but at that time I don't know the theorem of symmetric polynomials, but now I know this, so I can solve this. So how to factor this? Right? How to factor this? The problem is that you know that this guy is symmetric polynomial, right? Because you exchange with x, y, and z, but this is not the same as the usual symmetric polynomials, right? So in order to kill this x cube, right? So I know that it must be product of symmetric polynomial, right? So I can write. I mean, I can try. So these guys already a symmetric polynomial. S3 is x, y, z, and S1 is x plus y plus z. S2 is x, y, y, z, x, z, right? So basically for this, I don't need to worry about this because this guy is minus 3s3. How about this? So the problem is that we need to find a way, right? So what is the possible contribution, right? So one simplest should be S1 cube. Okay? Because S1 cube should contain S2 cube. Okay? And what is the remaining term? Right? So if you just spend this, you just do the expansion, you can x cube, y cube, z cube, and also other term, right? But let's do this. Let's spend this and let's try to compute this. But basically, you can write it as this, right? So this is, so you can write every of this in terms of the symmetric polynomials, right? So this guy will be S1 cube, S1 square minus S2, right? And then this guy is S1. Okay, so this is the power of 3, right? So you can expand it, right? But once you expand it, you notice that you get some cube, and plus this you get some cube, and plus there's some xy square, xz square, x square y, xyz, and x square z. Okay, and then you can check that you can also keep going and take the rest, right? So basically you need to do some computation, but once you use this previous algorithm, then finally you will arrive this. And then you can write it as symmetric polynomials, right? So this guy should be S1 S1 cube minus 2s2, right? So 3s2. So basically the remaining term is this S1 S1 to S2. Yeah. Okay, so should be final will be this one. Okay, and this 3xyz term will cancel from this. Okay, so this is the one example. Another example which is also very famous is called the discriminant. So for example, given any polynomial, okay, so this is very famous result. So given x1 up to xn, let's say you imagine which is the roots of polynomials, then you can define a so-called discriminant, defined to be this. So x1, xi minus xa squared, right? So obviously that d is symmetric. And these and also d plays important roles. Plays important role in the Galois theory. Also, you may heard about so-called solved by radicals. So basically, you can ask whether the square root of d inside your field, and you can determine the size of the Galois group, especially for the cubic. So basically, you can write it as this in terms of the coefficient of the polynomial. Let's suppose you consider your polynomial f to be, let's say, x minus xi, I from 1 to n. and then you can expand it in terms of coefficient. And then by our previous theorem, this will be a function of the coefficient. By the property of the symmetric polynomials. Right, so this is very, very famous application for the using the previous theorem. Okay, so that's it. See you guys next videos.